Good morning, all.
Good morning, ma'am.
Okay. So last class we have seen restoring method of division, right? And I also explained the procedure for non-restoring division method. Today we will see an example on that. So in restoring method, here, why the term restoring here means after subtracting divisor from the dividend, right? A minus B, after doing A minus B, if your A is less than B, that subtraction should not happen. So we are restoring the dividend back by adding the divisor to A. This is because of this reason it is said to be the restoring method. We need to restore the dividend back to A, right? So rather than adding back again to A, we have another method that is what called a non-restoring method. In restoring method, A minus B we are doing. If A is less than B, we will add B. Okay. In turn, in the next time around the loop, the next operation is shift left, right? So shift left is nothing but multiplied by 2. So this value, whatever it is there, A minus B plus B, that is shifted left. So it is nothing but multiplied by 2. After that, again, we are subtracting the divisor from the dividend or the partial remainder, right? So that we will be getting 2A minus B. Okay. So the same result which was obtained in restoring method, same result can also be obtained in non-restoring method by leaving A minus B as it is. Next time around the loop, after shifting left side, add B to it. Okay. If you add B to it, you'll be getting again 2A minus B, the same result. Okay. Rather than restoring here itself, rather than adding B here itself, I will shift left side and then add B, so that I'll be getting the same 2A minus B, which was same as in non-restoring method. Okay. Am I clear? So when we add B, when we have to add B, this condition, it is not necessary to add always B. When we add to B, when A less than B, then only you have to add B to obtain this result. Okay, right? Here also, if A less than B only, you are adding B. Otherwise, you won't restore, right? You'll proceed as it is, shifting left side and again subtracting B. If it is subtraction should happen, if your E value is 1, it means true subtraction, A greater than B, we won't add B here also. Okay. So whenever A less than B, then only you will add B, either in restoring or non-restoring method. Okay. So in restoring method, we will add B and then we will shift and then again subtract. Okay. But in non-restoring method, we won't add B, but first we will shift and then we will add B. Okay. So after shifting left side, right, whenever you shift left side, whatever is the value that was there in E flip-flop, right, the shifted left value, we will lose this E, which holds the value due to subtraction. This value we will lose in restoring method. Okay, right? So after shifting left side, whether you need to add B or not, how can we know whether we have to add B or not at this stage? Can anybody tell me? Am I clear? Are you clear with my question?
Ma'am, your voice is breaking, ma'am.
Breaking. Are you clear with my question?
No, ma'am.
No.
Your voice it's cut. It's getting cut, ma'am, in between.
Is it clear now?
Yes, ma'am.
Okay. See, we have to add divisor to the partial remainder only when A less than B. In restoring method, we are restoring based on the flip-flop E. Okay, if E is 0, it means A less than B. So we will add. But in non-restoring method, we are not restoring here itself. We will shift and then we'll add B so that to get the same result. But this addition of B has to be done only when A less than B. Otherwise, we should not do, right? So when we perform shift operation, the value available in E, we will lose. It will be replaced with the most significant bit in A. Okay. Then how would we know whether to add B or continue with subtracting B? Am I clear with the question? What is
Yes, ma'am. Yeah.
the answer? See, if A less than B, what is the quotient value Qn? That corresponding bit Qn at that particular time, Qn bit. How many times that B can be subtracted from A? If E is 0, 0 times, right? Okay, if your
Yes, ma'am.
Qn is 0, it means A less than B. So you have to add B. If Qn is 1, it means your A is greater than B. So I can subtract B from A. Right? So either E or Qn can give us the information of whether A greater than B or A less than B. Okay. Right. So here
Yes, ma'am.
we will lose E due to the shift operation. So we have to check the previous value of Qn. If it is 1, we have to subtract B. If Qn is 1 means we can perform the subtraction. So you can proceed for the next loop by subtracting B. If Qn was 0, it means the previous subtraction is not to be done. So you need to add B. Right? Okay. So in non-restoring method, B is subtracted if the previous value of Qn was 1 and B is added if the previous value of Qn was 0. Okay. Here there is no need of restoring the partial remainder, right? So this process saves a step of adding divisor if A is less than B. But it requires a special control logic to remember the previous result. We should know what is the previous result. What is the previous value of Qn with which we have to decide whether B need to be added or subtracted. Okay. So the first time the dividend is shifted, B must be subtracted, which is always to be done initially. Also, if the last bit of the quotient is 0, see, if the last bit of the quotient is 0, because we are not restoring, at the end, the partial remainder must be restored to obtain the correct final remainder. Okay. So let us see the flow chart. See, this is the flow chart for restoring method. A, of course, A and Q has to form the dividend. Okay, AQ forms the dividend. A upper bits of the dividend, the Q lower bits of the dividend. This is I have to correct. B or M, which gives us the divisor, right? Initially, we have to check A less than 0. It means if first n bits of A or greater than first n bits of m, I can say that we can conclude that the division overflow error, that step I haven't mentioned here, that is by default. Later on, if you are a less than 0, it means no values. This is decimal value for suppose, okay. There are no value available in a. If a less than 0, then shift left a q. It is just indirectly if you are a less than m. Okay. Initially, if a greater than m, we will make our division overflow flag as 1 and we stop the loop. Okay. So if a less than m, then only we'll shift it left side and then we will subtract b, nothing but your m. Okay. Right. This is in case of restoring method. In case of non-restoring method, if a less than m, it means the previous qn is equal to 0. We are subtracting, we are adding divisor to the partial remainder or the dividend. Okay. So we are shifting left and then we are adding the divisor to the dividend. A less than m or a less than b. 0. Both are same here, right? So we are adding here. After that, again we are checking whether a less than 0 or not. Okay. See, if a less than 0 here, we will make qn 0 and decrease the sequence counter and then repeat. If a less than not a 0, it means we are making q0 present bit as 1 and we are decreasing the sequence counter and then repeating. Okay. So here itself, if your a is greater than 0 or greater than m, then we will shift left. After that, we subtract. Right. So based on the previous value of qn, here the condition either you can add or you can subtract. This is restoring algorithm. See, let us see example. See, here my dividend is 46. I have taken simple values 46, 10, 110, and divisor is 0, 1, 0, 1, 1. 23 is the divisor, right? So since the number of digits here are 6 here and 6 here, so upper 6 bits dedicated for a dividend are 0. We have only 6 valid bits, so that will be loaded in Q register itself. AQ forms your dividend, right? So upper 6 bits are 0, only lower bits are allocated, are enough for loading your dividend. And right now here Q0 is 0, LSB of Q. And M is our divisor 0, 1, 0, 1, 1, 1, which is 23. Okay. Since in your algorithm, you may require to add M or add divisor or subtract divisor. So I need minus M also. So subtraction I can perform by adding 2's complement of M. For that I have calculating M minus M also. 2's complement of M, which is nothing but 1, 0, 1, 0, 0, 1. And the number of bits in your divisor are 6. So the sequence counter is 6. 6 digits of operation. Okay. And see, we are talking about sign magnitude data. Okay. Only the magnitude values we are considering. There is no sign involved here. Okay. And after this, we have to start algorithm. So in the initial table, first we need to shift AQ and leaving your new value of Q naught as a blank. Okay. After shift left, we will leave Q naught value as blank. Based on this result, in the next loop, we have to decide whether to add B or subtract B. Okay. See, this is your B and this is minus B. A, Q forms your dividend and the sequence counter. See, my dividend is loaded. See, dividend is loaded here. A, Q, sequence counter is 6. We are shifting left side, because here itself your A is less than B. So we can perform the division. We go by shift left. Initially, see here first time we have to perform the subtraction. Okay. So shift left side, leaving Qn initially as don't care. Okay. So here we are leaving it blank. Based on this result, we will decide whether this particular bit is 0 or 1. Okay. First time we are shifting left. After that we are subtracting. Right. So this is what your minus B. We are adding these two and we got this result. Okay. Right here we got this result. It means A is less than 0 here. There is no E bit here. Okay. So we didn't receive any E bit here. So A is less than 0. So I have to make my Qn 0. I made my Qn 0. Okay. This is first loop. After that, we are shifting left side second time and leaving the new Qn as blank. Since the previous Qn is 0, right? Previous Qn is 0. It means this subtraction should not happen, right? Okay. So, but we have shifted left so that we are adding B, non-restoring method. Right? See, initially we have to perform the subtraction. Right? Initially we have to perform the subtraction after shift left. After that, based on the E value which was obtained after subtracting, we are making your Qn either 0 or 1. Since here we didn't receive E, so I made my Qn 0. After that, shift left. Since the previous value of Qn is 0, I'm adding B. So that I got this value. Okay. Previous value of Qn is 0. So hence I have added B. Right. So here again, if my result is A less than 0, so I am making my Qn 0. Again, here I made my Qn 0. Again, shift left. Previous value of Qn is 0, so I have added B. Based on this result, if it is less than 0, I made my Qn 0. Okay. See, actually here it is not less than 0, it is less than B. Okay. So Qn is 0 here also. Again, shift left. My previous value of Qn is 0, so A plus B. Again, shift left. Previous value of Qn is 0, so A plus B. Likewise, till here, as and when we got here, our result we got it as 0. So we are shifting left because the previous value of Qn is 1. This is the correct one. See, after adding, we got our E as 1. So your Qn is 1 here, and then shift left, A greater than 0. So perform the subtraction because your Qn is 1 here, so you have to perform the subtraction. See, if whenever your Qn is 1, you have to perform subtraction. If your Qn is 0, you have to add. Right? Finally, you'll be having your remainder in A register, quotient in Q register. Every time reduce the sequence counter, as and when it becomes 0, complete the loop. Right? So this is restoring method. Only the thing that you have to remember, previous value of Qn. That's all. Okay, based on that, we can decide whether it is addition or subtraction. Right? Is it clear? Any doubts here?
Yes, ma'am.
Yes, ma'am.
No, ma'am.
Is about restoring method of sign magnitude data. Okay, of division. So this is about computer arithmetics, both addition, subtraction, multiplication, and division. Next topic is representing real numbers. That is nothing but floating point operations. Floating point representation. So till now we have seen integer, number, right? So numbers treating only as integers. So we know our numbers do have fractions. They may also have fractional part along with the integer. We call them real numbers. Okay, so we can represent them like this in binary. See, after decimal point, if you have any bits, we go by with the powers of -1 to power -1, -2, -3, likewise, and so on. Before the decimal point, we go by integer powers, positive powers, to power 0, to power 1, to power 2, to power 3, likewise. So this is what the number represents, 9.625, right? So, but how to store this number in a computer? How to store this binary point? Okay, where this binary point is stored. Okay, so based on the position of this binary point, we do have fixed point representation and or moving. If this decimal point is able to flexible to move over the register, then we call it as moving or floating point representation. So anyway, we have seen the fixed point representation where our decimal point is fixed at after LSB, after least significant bit. So such notation is flexible for representing only integers. Okay, right? There is another method which is there for fixed point notation where we can represent the fractional part also. In that case, my decimal point is fixed after MSB, after most significant bit. Here, my decimal point is fixed. That is what called fixed point fractional representation. Anyway, this is not there in your syllabus. Okay. So fixed point fractional representation, your decimal point is fixed after MSB. You know, MSB is mainly meant for sign of the number. See, your numbers apply here to power -1 to power -2. So the fractional part start with 0 point and x something. So this is the method used for representing fixed fractional part. Okay. So if your numbers have both integer and a fraction, we do have such representations in fixed point. That is what called a Q notation, which we'll be getting in a DSP applications on that. Right now, you don't have in your syllabus this methods. Okay. So just for your information, I am giving. Right. So in fixed point, we have our integer representations that we have done. If we want to represent the real point, then we have to go by floating point representation, where our decimal point will be floated anywhere within the specified number of bits. Okay, that is what called a floating point representation. For that floating point method, numbers are represented in scientific manner. Okay. So numbers are represented in scientific notation, where here S meant for sign, whether it is plus or minus, into B, it is what you are significant actually, right? and E meant for B is base, sorry. Here B is base and this is plus or minus. S meant for significant and E is your exponent plus or minus. B is base. See, for example, if I have a number like 2.56278, okay, right? So this is what my number. If I want a number like this, I can represent this as like 256 to 78 into 10 power, because these are decimal numbers, 10 power 1 2 3 4 5, 10 power minus 5, right? 10 power minus 5. Likewise I can write, okay, right? Or else I can write like this itself, 2 into 10 power 0. If I have a number like 303 into 7289, okay. So when I have to add these two numbers, then what should I do? I need to make both the exponents in same. Okay, here also it is 10 power 10, same, and then add, right? So this is this portion is called total portion. If you want, we can make it 303289 into 10 power minus 3. This is your significant, this is your base, this is your exponent, and sign of the number is positive. Okay, so this is what your scientific representation. Similarly, in binary, if I want to represent, I have to go by this method. There is a proper notation, proper standard for representing the binary in terms of binary word. That is what called IEEE standard. Okay. So typical, we normally use 32 bits for representing our floating point numbers. Okay. Out of the 32 bits, the most significant bit is reserved for sign component, and remain 8 bits are reserved for exponent, and 23 bits are reserved for significant. Okay, so 23 plus 8 plus 1, totally 32 bits. Okay, so this method, there is a standard, that is what called IEEE 754 standard, where the 32 bits are separated, like 23 bits for your significant, 8 bits for exponent, and 1 bit for sign component. Okay. So in this IEEE standard, IEEE 754, basically the standard name. Okay. IEEE 754. Okay. So in this, leftmost bit stores the sign of the number, 0 for positive, 1 for negative, and the exponent 8 bits are reserved, right? So even the exponent name is biased exponent, not just a simple exponent. Okay, right? See, biased exponent. What is biasing? I will tell you. The exponent value is stored in next 8 bits, and this is under biased representation. Okay, so the exponent is stored as true exponent is your true value, plus bias value gives us the biased exponent. Okay, right? You can write the equation in another way: true exponent plus bias gives you biased exponent. Okay, right? What is bias? It is a fixed value. Bias is a fixed value which has to be subtracted from the biased exponent to get your true exponent. Okay. See, whenever you have a number which will be having a positive exponent or a negative exponent. Okay. So you may have a positive exponent or negative exponent. Whenever you want to store that into a binary form, you need to take care of this positive or negative sign also. Okay. See, if your significant is positive or negative, we have a facility to consider the most significant bit, which is reserved for sign component. Okay, but in exponent case, there is no sign component separately, right? We should not give a sign component separate, right? So in exponent case, to have to store both the positive and the negatives, we are using biasing. Okay, so a bias is nothing but a fixed value which has to be subtracted from the biased exponent to get the true exponent. Okay, or else a bias is a fixed value which is need to be added to true exponent to get a biased exponent. Okay, so it is a fixed value which is added to be true exponent to make, even if the true exponent is a negative, we are making it to positive by adding something. Okay, while calculating back, you need to take care this expression. Okay, while calculating back what is your true exponent, we will subtract the bias value from the biased exponent. Okay, what is this bias value? Okay, so this value is decided based on the number of bits that we are dedicating for representing your exponent. Okay, if k bits are dedicated for representing the exponent, the bias value is 2 power k minus 1 minus 1. Okay, so as per here, we are reserving 8 bits. So the bias value is 2 power 8 minus 1 minus 1, which is nothing but 2 power 7 minus 1. 2 power 7 is 128. 128 minus 1 is 127. So the bias value is 127. Okay, and we know since 8 bits are there, our true exponent can range from, since my exponent can be have now positive or negatives. Okay, so for 8 bits I can represent till minus 128 to plus 127. Okay, so these are the true exponent values, right? So true exponent values are in range minus 128 to plus 127, right? So if your bias value is 127, when I add this 127, right? So when I add this 127 to it, I'll be making my values which are range from minus 1 to 255. Sorry, this should be 0. True exponent minus 127 to plus 128. Here I have a little doubt. As with the 8 numbers, I can represent minus 128 to plus 127, right?
Ma'am,
Yes.
they said from we can represent from 0 to 255 now, ma'am. So for each number, if we do minus 127, we'll get minus 127 to plus 128.
Okay, okay. Yeah, we have to come back from exponent. Biased exponent nunchi ravali. Sorry. Okay. So our biased exponent is 8 bit. So I can have a values 8 zeros to 8 ones. So which range from 0 to 255. If I subtract my bias value, which is nothing but 127, so then I'll be getting the true exponent values range from minus 127 to plus 128. Okay, so I come from true exponent, sorry. So I have to come from the biased exponent. So biased exponent, which is of 8-bit width, which can have a possible values 8 zeros to 8 ones. So in decimal 0 to 255, from which you have to subtract our bias value. So minus 127 then I'll be having my true exponent can range from minus 127 to plus 128. Correct, right? This is about Bayes component. And coming to the significant, we have 23 bits left that represent your significant. Okay. And next, coming to another important point in IEEE standard, normalization. So you may have any number which is having this, like this or like this or like this. Okay. So then what is the significant? Either it is 110 or 110 or 0110. Okay. So with if I take this number, the significant is different and my exponent is different. Here also significant different, exponent different. Okay. So, but all the values represent the same value, right? So to store any of your floating point number, which was expressed in many ways, to simplify this, there is a normalization is performed, right? A normal number is the one with which the most significant digit of the significant is non-zero, right? We have to perform normalization in such a way that we will consider the most significant digit of the significant as non-zero. So we are adjusting for base 2 representation. A normal number is therefore 1 dot all your bits. You need to adjust your any of the number in this manner. Then this is what we call as normalization. Okay. So this can be adjusted to 1.10 into 2 power. The decimal point is shifted left side by 1. So you need to multiply by 2 to get your original number. So 2 power 6, right? No. 1 dot, it is shifted, you have to divide it, right? So 2 power 4, this one. Here, you need to make 1.10. So the decimal point which was here, I need to shift it by left side, 2 digits. So I have to multiply by 2. So which is nothing but 2 power 4 here also. So here I have to move my decimal point here. So it need to be shifted right side by 2. So I have to subtract 2 from power of 2. So 1.0 into 2 power 4. Okay, so both are same now. This is what they call normalization. And this is what we call now as a significant. And this is your true exponent. Okay. And anyway, based on the value, whether it is plus or minus, that will take your most significant bit, where B is your binary digit here. Okay. So this will take 23 bits, and this is your true exponent to which you have to add Bayes value to get your biased exponent, and that will be stored. Okay. Right. This is what we call normalization of the number. So any number that we want to represent in 32-bit floating point format, that number first to be converted into binary and perform the normalization, get the significant values, exponent values, and get your biased exponent value and store it into your 32-bit number. Okay. Because we are doing normalization before storing every number. So the most significant bit is always 1. It is need not to store that one every time. Okay, only the 23-bit field is used for storing. Okay, so with which we will be having a possible value in a half open interval, 1 to 2, right? Because we have to 1 dot all B's, right? So here we need to apply power of 2 to power minus 1 to power minus 2 to power minus 3 and so on. Okay, so you'll be getting 1 plus B into B by 2 plus B by 2 power 2, B by 2 power 3 plus and so on, B by 2 power n number of bits dedicated for storing your significant. If all the B's are 1, then I am checking for the maximum value. If all B's are 1, then I'll be having 1 plus 1 by 2 plus 1 by 2 square and so on 1 by 2 whole power n. Okay, what we call this a plus a square plus and so on a power n. We'll be having, if your a is less than 1, then I can take it as 1 plus a square. I can take it as
1 minus 1 by 2 power n.
1 minus
1 by 2 power n
1
by
by
1 by
2
2.
whole power n plus 1. Here we have n terms, right?
Yes, ma'am.
By 1 by
1 by
1
2.
minus 2. This is equal to half. So that will be, here it is 2. Okay. So 2 minus 2 power minus n minus 1 into 2. Okay. So it is equal to 2 minus 2 power minus n. Very less portion of 1 by 2 power n. See, if I am using 23 bits for storing my mantissa, so how much is 1 by 2 power 23, which is very, very less value, that we are subtracting from 2. We won't approach to 2. So hence I didn't use a closed interval, closed braces for 2. Open braces means 2 will not be in the range. Okay. So it will approach us to 2. It won't approach anyway every time. Okay, is that clear? This is the range of significant that we are taking. In IEEE 754, 32-bit representation, we call this also as single precision. This is also the name called single precision method. Single precision representation. Okay. So this is just a summary. Sign is stored in the first bit of word, right? And first bit of the true significant should be always 1. First bit of the word store the sign component, which is the most significant bit. And first bit of the true significant is always 1. We are not storing this one anywhere. It is implied, okay? And need not to be stored in the significant bit. The value 127 is added to the true exponent to store in the exponent field, which is of 8-bit width. Okay. And the base is here 2. So now expressible numbers. So we were now comparing the range of numbers that we can represent for fixed point, and we are now comparing with the floating point. Right. So let us see for integer representation, where our numbers can take both positives and negatives. So 2's complement integer representation. So if I use 32 bits, right? So if the same 32 bits I am using for representing my numbers in fixed point format, that too integer representation, right? So I can have a range minus 2 power 31 to 2 power 31 minus 1, correct? Right? See, if it is 8
Yes,
bits, 8 bits, I have minus 2 power 7 to 2 power 7 minus 1. Okay, why 7 we got? Because the most significant bit is the sign bit. Remaining only 7 bits are used for magnitude calculation, right? So hence 7 only we got, right? So similarly here 32 bit, 1 bit is most significant, remaining 31 bits represent your magnitude. So the range of values minus 2 power 31 to 2 power 31 minus 1. This is the expressible integers in fixed point notation, 2's complement integers. If we see now for floating point 32-bit formats, see in 32-bit formats, we know this is 1 significant bit and 8 bits reserved for exponent, biased exponent that too, and 23 bits are reserved for significant. Okay. So we have concluded that the significant range is 1 to 2, approximately 2, right? And coming to this, what is the exponent values? Exponent can have, see, negative numbers will be now between, see this 2 how we got, this 2 is 2 minus 2 power n, right? We have just now calculated the maximum value. 2 minus 2 power n. N is nothing but number of bits that we are dedicated for storing your significant.
Minus n, ma'am.
Yeah, sorry, 2 power minus n, right? So 2 minus 2 power minus 23. To get negative numbers, your significant will be minus, right? So I am adding minus into maximum exponent. Maximum exponent, true exponent is 128. Least exponent is minus 127. Okay. So negative numbers will be now have with exponents minus of 2 into 2 power minus 23 into 2 power 128 or minus 2 power minus 127. Okay. So from here to here we have our negative numbers, right? Since our significant can be 1 to 2 minus 2 power minus n, significant, right? So if you are adding sign to it, negative numbers, it is minus 1 to minus, right? For that, we are adding now your exponent to have a least value. I'll be adding 2 power minus 127 here, 2 power minus 127 here. To have a maximum value, minus 1 into 2 power plus 128 and minus of 2 minus 2 power minus n into 2 power plus 128. These are the 4 possible values that we come across after adding all the extreme conditions. Now, based on the values, you place where are these values. See, the first value, if you take minus 1 into 2 power minus 127. Okay, it is just nothing but minus 2 power minus 127. Okay, so this is the value. And next 2 minus of 2 minus 2 power minus n into minus 127. So this where this value in the number line, can you detect where this value occurred? It is 2 minus 2 power minus n. It is approximately, it approaches to 2, right? Minus 2 into, if I take it as minus 2 into 2 power minus 127. Okay, which is nothing but minus 2 power minus 126. So which is approaches to 2 power minus 126 is beyond this, right? Negative number. So this will be around here. This value will be around here. Am I right?
Yes, ma'am.
Next, minus 2 power 128. Minus 2 power 128. This will be around here. Positive one. After that, last value minus 2 into 2 power 128. This will be this value. Okay. So this is the range of negative values. Similarly, range of positive values. Okay. See, by observing this, you cannot represent a value in between 0 to this value. So this we call it as a positive underflow. Similarly, negative underflow. If you have your numbers still lesser than this exponent, okay, lesser than this exponent, let us suppose 2 power maybe minus 200. 2 power minus 200, a positive 2 power minus 200 will be somewhere in between these two. You cannot represent this much lesser value, then we call it as positive underflow. Similarly, we have negative underflow, right? And positive overflow, beyond this, if you want to represent, you cannot do positive overflow and even negative overflow. Okay, and these are the values that we can represent. Anyway, just by observing the range of values, this is 2 power 128. But if you see for fixed point, the range of values, they are powers of 2 power 31, right? Here it is 2 power 128. We can have a large range, right? The range is more in case of floating point. We call that as a dynamic range. Number of values that we can represent in with respect to floating point is very high when compared to fixed point notation. Is that clear?
Yes, ma'am.
Okay. So, and those 5 regions wherever we cannot represent, they have the specific terms. We call them as positive overflow and negative overflow, positive underflow, negative underflow. Okay. So 5 regions on the number line which are not included in the floating point representation are negative numbers less than this value, negative numbers greater than this value. Similarly, 0 also we cannot represent. See, for representing 0, we didn't have any notation. Okay, we don't have any format, any bits dedicated for representing 0, right? Because the implied significand is 1 dot, right? So we are normalizing our numbers such that we have a significant which starts with 1 dot. So 0 never we cannot represent, right? Am I clear?
Yes, ma'am.
So 0, positive numbers less than this, positive underflow, positive numbers greater than this are positive overflow. See, but out of this, all these can be expressible, but 0, which is a very important number, right? Okay, without which we may get a results of 0. You may want to take a number as 0, but 0 has to be represented at any cost, right? So to have this notation to represent, to give facility for representing 0, there are certain adjustments that are done for IEEE standard. In case of IEEE 754 standard, which was adapted in 1985. We have 2 standards in IEEE 754, single precision, which uses 32-bit, double precision, which uses 64-bit. This we will see a bit later. Okay. So, see, this is what the adjustment. See, the adjustment representing 0, we'll see in next class anyway. So let us see how a numbers can be represented in 32-bit with examples. Today we'll take one simple example. Consider, forget about this slide, we'll come to this later. So let us suppose I have a number, maybe 2.5. I want to represent 2.575. Okay. So consider this number 2.575. So what is, if you want to store this decimal number in computer in binary format, first you have to convert it to binary, right? So 2 is 10, and let us suppose our number is positive. Okay, my number is positive. Okay, so 10.575 in decimal. How can you perform? In decimal, you have to multiply this by 2, right? So 0.575 into 2. Right, 105. So we'll be leaving 1 and 0.5 into 2 into 2, which is nothing but 0.1, 0, and 0.1 into 2, 0.2, 0, 0.2 into 2, 0.4, 0, 0.4 into 2, 0.8, 0. So 0.8 into 2, 1.6, 1, 0.6 into 2, 1.2, 1, and again 0.2 into 2, 0.4, it repeats. The cycle repeats from here continuously. Okay, right? So we'll be having a fractional part 1, 0, 0, 0, 1, 1, again 0, here 0, right? So 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Likewise, it will be repeatedly continuous, okay? It won't stop at any instant, right? Am I clear?
Yes, ma'am.
It forms 2.575. Okay, so this number you need to represent it in a floating point format. So what is the first thing that we have to do? You need to normalize this number, right? Okay, so for normalization, what is the procedure? You have to bring your decimal point after a non-zero most significant bit. That is nothing but you have to adjust this to 1 dot 0 1 0 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0. Likewise, you have to take how many bits? How many bits I can take? These are the significant portion, right? How many bits we are reserving
Yes.
for reserving significant? 23 bits.
Three.
Okay? So till 23 bits I can take this continuously into what is the base? 2. What is the true exponent? True exponent,
1.
how much?
1.
Plus 1.
Yes, ma'am.
Plus the decimal point is shifted left side. So true exponent is plus 1. Okay. So from this is what you are, now we got our number into scientific notation. Now from which you have to extract the significant portion. So what is the sign component? Sign component here is positive. So the most significant bit is 0. And next the significant. So the significant 23 bits you have to take from which. Okay. So 23 bits 0, 1, 0, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Likewise, you have to extend till 23 bits. Okay, extend it to 23 bits. This is your significant. Now coming to actual, true exponent is plus 1, which is nothing but 0, 0, 0, 0. 0, 0, 0, 1. And we want biased exponent to be represented, to be stored in your 32-bit format. So biased exponent is, you need to add 127 to true exponent to get biased exponent. Okay. So 127 you have to add. 127 is 1, 1, 1, 1, 1, 1. How much is 127? Sorry,
7 ones.
0, 7 ones. Okay. So after adding this, I'll be getting 128. So your exponent is 1, 0, 0, 0, 0, 0, 0. Okay. So these are 8 bits. These are 23 bits. And this is 1 bit. So combinedly, I'll be getting 32-bit floating point number. And what is that total 32-bit? If I write, I'm writing here. The most significant bit is 0. And then our biased exponent is 1, 0, 0, 0. Right? And then our number significant 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. Likewise, 32 bits. Okay. So 9, 10, 11, 12, 13. Oh, sorry. 17, 18, 19, 20, 22, 23. Okay. So this is your 32-bit representation for the number 2.575. Okay. So this is how you have to convert. Is it clear?
Yes, ma'am.
So this is reverse. If you have given a number, if you have given any number like this, right? What is its corresponding decimal number? You need to go by reverse procedure also. Okay. Right? Practice both examples converting from decimal to floating point IEEE standard, and whenever you have given IEEE standard 32 bits, now what is the number that it is represented by it? Okay, that also you have to consider. And what are the adjustment letter they have taken for representing 0 and plus infinity, minus infinity also. Okay, that we will see next class, right? So this conversion procedure is important, Amma. Compulsory question, both the cases. So is there any doubts?
No, ma'am.
Please wait. Let me take the attendance. Can you read out the attendance for me?
Yes, ma'am. Absentee numbers, ma'am.
Yeah, just absentees so that I will note down.
65,
65.
67,
Yes. Next.
79,
Okay.
90.
90.
Yes, ma'am. 93,
96.
93, ma'am. 101,
Okay.
113, 114, 115, 116, 120. That's it, ma'am.
Thank you, ma'am. ఈ నెంబర్ లేదనుకుంటా. Okay. Thank you, ma'am. Bye for today.
Thank you.